Professor Curtis, and this is the lecture video for Chapter 35, Special Theory of Relativity. Let's get started. So, to start off with understanding Einstein's special theory of relativity, we need to talk about the relative nature of motion. So imagine that you're sitting on a bus. The bus is traveling at 80 kilometers an hour, and the speed at which you're going will depend on your perspective. So, for example, relative to the bus, you're not moving because you're moving with the bus. So, relative to the bus, from that perspective, you're not moving. However, from the perspective of someone standing on the ground, you're moving at 80 kilometers an hour because you're moving with the bus, you're moving at the same speed as the bus, and so you have 80 kilometers per hour from the perspective of the ground. If you're looking from the perspective of someone standing on the surface of the sun, never mind the fact that someone would actually get burned up, not even getting close to the surface, let alone being on the surface. Okay, so you can see that that the speed at which you're traveling is going to be a lot greater. Okay, now it could be 108,080 kilometers per hour, or it could be 170,040 kilometers per hour, depending upon which way the bus is moving relative to the direction of the Earth moving around the sun. But be that as it may, it's still a lot bigger than if you're looking from the perspective of the bus or the perspective of someone standing on the ground. So it depends on where we actually observe motion from. And so the place at which we observe motion from and measure is called a frame of reference. So because motion is relative, its value will depend on what you use as your frame of reference. What perspective are you taking on the situation? So this concept of frame of reference helps us to measure the speed of an object. So in order to measure the speed of an object, the first thing we have to do is choose a frame of reference. What perspective are we going to take for making our measurement? Once we've chosen our frame of reference, then we need to pretend that we're inside that frame of reference and we're sitting still. So what we're going to do is we're not going to be moving ourselves, but we're going to be inside this frame of reference and we're going to be sitting still, observing the motion of the object whose speed we're trying to measure. And then we just go ahead and measure the speed that object moves relative to ourselves. Okay? And because we're standing still inside that frame of reference, that speed will be relative to the frame of reference in which we're sitting. So here's an example of how this works. Imagine we have a person who's inside a train. The train is traveling at 60 kilometers per hour with respect to the ground, and this person inside the train is walking with a speed of 1 kilometer per hour with respect to the train floor. The person is walking towards the front of the train. So the direction of motion for the person inside the train is the same as the direction of motion for the train itself. What is the speed of the person in the following frames of reference? So if our frame of reference is inside the train, what will the speed of the person walking inside the train be? Well, it should be pretty clear that that's going to be 1 kilometer per hour. If you're sitting with respect to the train, then you're going to be moving. You're going to watch this person move at the same speed that he's moving with respect to the train floor. But if we shift our frame of reference to the ground, well, now the person inside the train is going to appear to be moving at a rate of 61 kilometers per hour. The train is moving at 60 kilometers per hour with respect to the ground, and then you add in the 1 kilometer per hour with respect to the train floor. So the person inside the train is going to be observed to move at 61 kilometers per hour. What about from the perspective of a bicycle traveling 10 kilometers per hour towards the train? Well, the person inside the train is then going to be observed to be moving 71 kilometers per hour. 61 kilometers per hour with respect to the ground, and the bicycle moves 10 kilometers per hour with respect to the ground. Where do the negative signs come from? Well, the first negative sign comes because the two objects are moving in opposite directions. So they're moving towards each other. Whereas notice with respect to the ground, we added two positive numbers together. That's because both the train and the person inside the train are moving in the same direction. So the first minus sign there comes from the fact that we're moving towards each other. The second minus sign comes from the fact that the direction of the bicycle is opposed to the direction of the train. So remember before, early on in the course, we were talking about vectors, and each of these vectors have a magnitude and a direction. Well, the vector for the speed of the bicycle is opposite of that with the train. So if we assume the train is moving in a positive direction, then the bicycle must be moving in a negative direction. So the second minus sign comes from the fact that you're looking at moving in the opposite direction of the train. So the two minus signs cancel. 61 plus 10 gives us 71. This concept of motion being relative and depending upon your frame of reference leads us to Einstein's special theory of relativity. Now you might be wondering, why are we studying special theory of relativity before the general theory of relativity? Well, that's because Einstein didn't know his special theory of relativity was for a specific case until he came to a point where he was trying to use the correspondence principle that we talked about in a previous lecture with Newton's laws of motion. We'll get to that here at the end of this lecture. So it wasn't until then that he knew that he was dealing with a special theory of relativity. But that being said, the first postulate that Einstein made when developing his special theory of relativity was that all laws of nature are the same in all uniformly moving frames of reference. What this means is that motion is relative to arbitrary frames of reference, not to any absolute frame of reference. So the quantity of motion that we have, the direction of motion that we have, it's all relative to the perspective that we take. So if you're aboard a rocket ship, you can't measure the speed of the rocket relative to space. You can only measure the speed of the rocket relative to other objects. Okay? So to kind of imagine what this is like, think of the disorienting feeling of watching another car pull away. Okay? So if you're in a car and you're seeing another car, pull away from you, and you kind of forget about where you are, but just focus on the car that's pulling away, you feel a little disoriented with that. And that's because you can't really measure your speed relative to the space around you. You can only measure it relative to other objects. So if you're in a car and you're moving, you can measure your speed relative to the objects that are on the ground. So those are objects. You measure it relative to the ground, but you can't measure it relative to space itself. So you can't look out in the air and say, oh, yeah, okay, we know how fast we're moving, because there's nothing there for you to measure your speed against. You have no frame of reference for that. Now, one of the fallouts from Einstein's first postulate here is that the laws of physics within a uniformly moving frame of reference are the same as those in a stationary laboratory. And this should make some sense if we think about the concept of equilibrium. Remember early on in the course where we talked about how you can have static equilibrium and dynamic equilibrium. But one thing is the same, is that whether you have static equilibrium or dynamic equilibrium, your speed is constant. So if you're not moving at all, your speed is constant. It's constantly zero. And so you're at rest. But if you're moving at a constant rate, so you have no acceleration, but your velocity is not zero, you have dynamic equilibrium, you're still in a state of equilibrium. So the laws of physics within a uniformly moving frame of reference. So if your frame of reference is in motion, but there's no acceleration, then you're going to get the same result that you would get in a stationary laboratory, a frame of reference that's not moving. This is why you can pour a beverage normally in a moving airplane. Gee, what would it be like if you try to, pour out your soda into a cup when you're sitting here in an airplane and the laws of physics were different? I mean, yeah, you make a mess really quickly. The second postulate that Einstein extended in his special theory of relativity is that the speed of light in free space has the same measured value for all observers, regardless of the motion of the source or the motion of the observer. In other words, the speed of light is a constant, irrespective of your frame of reference. So it doesn't matter, what you're looking from. So motion is relative, depending upon your frame of reference, unless you're looking at the motion of light. This is something phenomenal, because remember, it was the speed of light that says that energy and mass are one and the same. It was the speed of light that we could calculate theoretically from Maxwell's equations that helped us to understand that there's a connection between the speed of light and the speed of all electromagnetic radiation. And so this particular value is one of nature's constants. And it doesn't matter what your frame of reference is, it will always have the same value. So if you have a flashlight that's being shined towards you, the light is moving towards you from the flashlight at a constant velocity. But if you go towards that same light, now instead of being, standing on the ground, now you're actually moving towards that light in the flashlight on a rocket ship, the speed of light is still going to be the same. And, if you're looking back, if you're actually moving the flashlight away from you, the light coming from the flashlight towards you is still going to be one and the same. So it doesn't matter what your frame of reference is. Speed of light will always be constant. This leads us to the principle of simultaneity, which basically says two events are simultaneous in one frame of reference, need not be simultaneous in a frame moving relative to the first frame. So consider, for example, the case of a light in the middle of a rocket ship. So if you're sitting in the rocket ship and you're sitting there in the middle of the rocket ship with the light bulb, so the light is going to go towards the front and the back of the ship. And because light has the same velocity, no matter what your frame of reference is, it's going to hit the front and the back of the ship at the same time. And then the reflection from the inside of the ship will come back to meet the eye of the observer there with the light bulb. And the light that came from the back of the ship and the light that comes from the front of the ship will reach the eyes of the observer at the same time or simultaneously. Now let's consider that same rocket ship, but now we're going to change our frame of reference to someone who's standing outside the rocket ship. Now, the light that comes from the back of the ship is going to reach the observer at a different time than the light from the front of the ship, because the rocket ship is actually in motion. So the total distance the light travels to the back and then to the observer is going to be shorter than it is to go to the front and then back to the observer. This gives us the concept of space-time. The space we live in is three-dimensional, so we could actually use three numbers, which basically represent distances along three perpendicular axes, which we label x, y, and z, and we can use this to measure the position, or rather specify the position of any point in space. So we're going to go some distance along the x-axis, and then we'll go some distance parallel with the y-axis, and then we'll go some distance parallel with the z-axis to arrive at a specific point in space. So 3 numbers can define or specify the position of any point in space. And 3 dimensions can also be used to specify the size of objects. So you've got length, width, and height. Then we can use those to specify the size of an object. But there's a 4th time that we need to consider, and that is time. Because an object may be in one position at one point in time, but have a completely different position at a different point in time. Or it could have the same position at a different point in time. So there's a 4th dimension here that we need to consider, is time. And this brings us to the idea of space-time. We just can't describe space without also implying a sense of time. So things are existing in space-time. Things actually exist in 4 dimensions. So if there is relative motion between observers at speeds that approach the speed of light, those observers will not agree on measurements of space and time, okay? Because there's going to be a difference relative to your frame of reference. Now, these differences are usually imperceptible at relatively low speeds. So the speeds at which we're familiar with in our common experience, the speeds at which we move, at which we see objects around us move, these are much, much lower speeds than the speed of light. And so the differences between frames of reference are going to be much less perceptible. But when your speed approaches the speed of light, differences in frames of reference for moving objects are going to become more and more perceptible. So the thing that unites everything is the speed of light. Because again, remember, the speed of light is constant regardless of your frame of reference. And so that's the thing that connects the differences between moving objects from different frames of reference. This brings us to the concept of time dilation. So suppose again we've got an observer inside a rocket ship, and in the center of the rocket ship we have 2 mirrors. So we shine a light, get a flash of light into one mirror, and it bounces back to the other, which then bounces back to the first, and it just keeps bouncing back, so on and so forth. Okay, so it's kind of like this setup here, where we've got a flash of light that gets sent between 2 mirrors, and it just bounces back and forth. So for an observer inside the ship from that frame of reference, you're going to see the flash of light move straight up and straight down between the 2 mirrors. Okay, the same as if the rocket ship were not moving at all. Now, let's say we take a different frame of reference. Now we look from the perspective of someone outside the spaceship. From outside the spaceship, the path that the flash takes is not straight up and down. Now the path the flash takes is a series of diagonal lines. So from this frame of reference, the path the flash takes is longer than the path that's taken from the frame of reference from someone inside the rocket ship. But light, in both cases, remember, the speed of light is constant regardless of your frame of reference. So there's going to be a difference in time that it takes for the light to flash between the 2 mirrors depending on your frame of reference. And this stretching out of time is what we call time dilation. So time dilation is this difference of time depending upon your frame of reference. Now, this may sound, a little quirky, but time dilation is actually a real effect. So clocks in a moving frame of reference will appear to run more slowly when observed from a stationary frame of reference because of this time dilation effect. Back in the 70s, there was an experiment that was conducted to test this idea of time dilation. So 4 cesium beam atomic clocks were placed on 4 separate aircraft. Okay, the aircraft were then flown on a round trip. Okay, first westward and then eastward, and they were flown different distances. That's why they were doing the 4 planes. So each plane is flying first westward and then eastward, but they go different distances. And then the idea is that once these four planes bring their clocks back, okay, you take the clocks, you put them together, and you compare them with a standard at the U.S. Naval Observatory, which didn't go anywhere. So it's the stationary, it's the control. And what they found is that all four clocks were reading slightly different times. So the ones that were in the planes that went further out, okay, so they had a longer trip, okay, they were actually running more slowly than those observed from the stationary frame of reference, from the clock that didn't actually move. And the difference in the time between the stationary clock at the U.S. Naval Observatory and each of the individual clocks were exactly what Einstein's theory predicts. And so this experiment actually proved that time dilation is a real effect. GPS satellites actually rely on time dilation to convey accurate positioning. So if you didn't have time dilation, then a destination that your GPS shows you is a half-mile away would actually be shown in your GPS as being off by 5 miles after only 1 day. So without this time dilation, the GPS technology that a lot of us use and rely on every day would not be possible. Now, this concept of time dilation doesn't make sense to some people. Actually, it doesn't make sense to a lot of people. But, part of that is because the way we understand things as human beings is to compare what the new thing that we see with what's common in our everyday experience. And the speeds at which we're talking about here, in which time dilation really becomes powerful, are outside of our common experience. Okay, so we could fly in an airplane, but most of us aren't flying in airplanes all the time. Most of us are more commonly moving at much slower speeds. It's only when you get up to speeds that are faster, and especially at speeds that approach the speed of light, that this time dilation effect becomes more perceptible. That said, there's been repeated experiments. I mean, the one we talked about here is just, one of multiple experiments that have been conducted. They all prove that time dilation is a real effect. Which brings us to the Lorentz factor. So, Einstein's theory predicts the difference in time delay due to this equation that you see here on the screen. So, the time is going to be equal to the time that's observed, which is t0 or t0, and then you're going to divide that by the square root of 1 over v squared c squared. And v is going to be the speed of the moving frame of reference. C, of course, is the speed of light, and t is the time observed in another frame of reference. Okay, usually usually it's going to be a stationary frame of reference. This denominator that you see there, that factor there with the square root sign, appears very often in relativistic equations. And so we use a shorthand representation, so we don't have to keep writing all that out all the time. We just set the denominator, their portion, equal to a Greek letter, gamma. Gamma is the symbol that we use to represent that special factor, which is going to be called the Lorentz factor. So this part here in the denominator is what we use. We call that the Lorentz factor, and we represent it with the Greek letter gamma. So we could rewrite the same equation for time as t equals gamma t naught. And this is much more shorter and easier form of the equation. And as I said, it's called the Lorentz factor. It was named after Dutch physicist Heinrich Lorentz, who laid the foundation for Einstein. And you can see a picture of Lorentz there on the screen. The picture there on the bottom, he's standing there with Einstein. They actually knew each other and conversed with each other. They get together and they talk about their physics stuff. And so, this Lorentz factor shows up again and again. And we're going to see that here in this lecture and also in the next lecture. Let's demonstrate how to run a calculation with the Lorentz factor. Suppose we have a spaceship moving at 50% of the speed of light, and there's a clock aboard the spaceship. So an observer inside the spaceship will not observe any deviation in time because the motion of the observer relative to the clock is pretty small compared with the speed of light. So, will an observer outside the spaceship also observe no deviation? That's the question. Well, to answer this question, we have to use that time equation that we showed earlier. But if we find that there is no deviation, will the clock appear to run slower or faster to the outside observer? So, let's answer the first question, and we start by writing out our equation here for time, and then we're going to substitute in the values that we know. So we know that we're moving at half the speed of light, so our velocity is 0.5 times c, and we're going to square that quantity. Well, 1/2 c quantity squared is going to be 0.25 c squared. And then notice in that fraction there, we've got a c squared on top and a c squared on bottom. So that's going to cancel each other out. And then 1 minus 0.25 gives us 0.75. And then we can take the square root of 0.75 and then divide it into to get 0.866. And then, of course, we flip that around by dividing 0.866 into 1, and we get 1.15. So the time in the moving frame of reference is 1.15 times the time in the time in the stationary frame of reference is 1.15 times the time in the moving frame of reference. So to an outside observer, the clock inside the spaceship will appear to move 15% slower. In other words, for every hour of time that passes, the clock will read 9 minutes slow. Now, this is from the perspective of an outside observer. For an observer inside the spacecraft, there's not going to be any difference of time observed. So, now what I'd like you to do is to take that concept that we just learned about, and in your workbook, complete the following activity. Okay? So we worked an example problem where a spaceship was traveling at 50% of the speed of light. And we saw that an observer outside the spacecraft would observe a clock inside the spacecraft moving 15% slower. Well, if the spaceship now moves at 80% of the speed of light, will an outside observer still witness a difference? Will it be slower? Will it be faster? If so, by how much? Go ahead and stop the video here, and then when you get done, come back and we'll see how you did with that. Okay, let's see how you did with this. So we have a spaceship that is moving at 80% of the speed of light. So we start with our time equation, and we're going to plug in the 80% of the speed of light for our velocity. So then 0.8 times c squared is going to be 0.64 c squared. And so we have a c squared on top and the bottom. They cancel out. That leaves us 0.64. 1 minus 0.64, 0.36. Square root of 0.36 is 0.6. 1 divided by 0.6 gives us 1.67. So this tells us that to an outside observer, the clock inside the spaceship appears to move 67% slower than one that would be right next to the outside observer. So you're going to be moving, losing about 40 minutes for every hour. So this Lorentz factor has a huge influence on time. So if you can see from the table here that the closer we get to the speed of light, the bigger that Lorentz factor gets, and the more time is lost per hour relative to the time on a stationary clock. So for every hour that we spend in a relatively stationary frame of reference, there's going to be a perception of lost time in the moving frame of reference. So from a relatively stationary frame of reference, a clock in a moving frame of reference will always seem to move slower. If we take and make the clock move at exactly the speed of light, then the clock would appear not to be running at all. It would be so slow that it wouldn't seem to be running at all. It would seem like, is this thing even working? This brings us to the twin paradox, because this is a common example that's used to illustrate the effect of time dilation. So let's say we've got one twin, and who takes a high-speed round-trip journey while the other one stays at home on Earth. So one twin decides to say, I'm liking the ground, I'm going to stay here. The other one's too adventurous, like, no, I have to search the stars, and, go, boldly go where no man has gone before. So, you've got the astronaut flying off into space, okay? Well, eventually, the one that went off into space comes back. And when he comes back, he finds that he hasn't aged that much. But his brother, who he left behind, wow, time really passed for him. That's because time dilation says that time in the moving frame of reference will appear to go much, much slower than for the stationary frame of reference. So as the brother who stayed on Earth gets older, time seems to slow down for the brother who was in the spacecraft. And so he doesn't appear to age as much as the brother who actually stayed home on Earth. Does this sound crazy to you? Well, if it does, you're not understanding this concept of time dilation and the influence of the Lorentz factor. Okay? Remember, time dilation has been experimentally verified, so it's a real effect. And while you may not understand exactly the logistics and the mechanisms of how it works, you can at least accept, if only on a faith basis, that this is a real effect, and we need to account for when we're dealing with relativistic calculations. So here we've got a video. We're going to watch this video and check out. Basically, this is a good video that gives us a good overview of everything that we've been discussing so far. So hopefully I can get this to work here. See if we can. Oh yeah, here we go. So we're going to start the video up, and we're going to check this out. If it'll load. Hopefully it'll load. Tell me it'll load.
Time. You can't see it, you can't hear it, you can't weigh it, but we experience it every moment. The whole piece of time is a landscape, and we move through it, slice by slice. But do we really understand time? Is time same for everyone? To understand time, let's go back in time and make a small journey with a certain young patent clerk, Albert Einstein. Imagine you're traveling with Einstein in a train moving at a certain uniform speed. The train, relative to the outside environment, is in motion. The two of you sitting inside, on the other hand, observe each other as stationary objects, as both you and the train are moving at the same speed. Hence, relative to the train, you are stationary, and the laws of physics stay same inside the train as they would on the ground when you are standing still. Now, let's consider you get off the train and observe it moving across in front of you. Now, you are stationary, and relative to you, Einstein is moving with the same speed as the train. This is the phenomenon of relative motion, and we observe it every day. Does everything in the universe observe this relative motion the same way? Yes, everything except light. Light behaves in a different way. Imagine you have a light clock with you. This light clock has two mirrors in the opposite directions and a light beam bouncing between them. Now, let's say the distance between the two mirrors is d, and the time for the light to cover that distance is t. For the sake of simplicity, let's say it's 1 second. So, When this clock is with you at rest position, the light bounces between the mirrors, covering distance d in 1 second, which gives us the speed of light s. Now remember, speed is distance per unit time. Now consider Einstein also possesses the same light clock with him. Only this time, he's traveling in a spaceship along with the clock. When Einstein travels in a certain speed, the clock travels with the same speed of the spaceship in the same direction. Here, light has to travel an extra distance in the same 1 second. Let's consider this distance to be capital D and represent the speed of light here as capital S, which has to be greater than small s. But something's wrong here. Because in the late 1800s, the Michelson-Morley experiment tried to detect the relative motion of the matter through an ether and concluded that the speed of light is constant. This cosmic speed limit is known as c. So in our little scenario, small s and capital S are equal. So for the speed of light for both you and Einstein to remain constant, something has to give way. That something is time. It turns out, time slows down when you travel faster and faster, nearing the speed of light. So the faster Einstein travels, slower the time passes for him. Hence, what could be a day for Einstein in space could be as much as 50 years for you on the ground. This became the fundamental conclusion of the theory of relativity, a theory proposed by Albert Einstein in 1905. This theory broke the traditional understanding of time as a constant entity and proved that time, in fact, is different for different observers. The theory of relativity led to many other invaluable findings, the most famous of which is the equation E equals mc squared. But more on that later.
Yeah, so we've got a pretty good review there of the concepts that we've studied so far, and kind of a nice little piano jingle there at the end. So now we're ready to move on and talk about, if I can move on. There we go. So now we can talk about differences in length, because not only do we see differences in time, we see differences in length. Because remember, everything exists in space-time. We need time in order to define space. So because everything exists in space-time, it's not just time that's changing, it's also length that can change also. The distance that we're moving with respect to any of those three axes by which we used to define a position in space. So the faster we move, the more we approach the speed of light, okay, the bigger our Lorentz factor is going to get, and the shorter objects will appear to be. So in accordance with this equation here, okay, where we've got L equals L naught over gamma, L is the length measured in the moving frame of reference, and L naught is the length in the stationary frame of reference. So we can see here that the faster you go, the shorter or more contracted your object is going to appear, but only along the axis that's parallel with the direction of motion. So if you look at, a baseball that's moving there and see how it gets flatter and flatter along the direction of motion, if we were to take that same baseball and look at it from a different perspective, then it wouldn't seem like it was shorter at all. Okay, so if we're actually standing behind the baseball and we're looking at it as it's going away from us, it would still appear to be the same sphere that we know a baseball to be. But looking at it from the side, okay, now it looks like it's getting shorter and shorter and shorter as it approaches the speed of light. And eventually, if you actually could reach the speed of light, the object would appear to disappear entirely. So we perform the same calculations with length that we get with time to get the same sort of effect. Things get shorter in the direction of motion that are in that moving frame of reference. So what happens when the object moves at the speed of light? Well, eventually it just contracts until it just reaches nothingness. It just disappears. Sound funky? Well, it is. But it leads us to the concept of relativistic momentum. So if time and length are relativistic measurements, okay, it's going to vary depending upon how fast you're going and what speed of reference you got. Well, then motion itself is relativistic, because by definition, the speed is the change of distance with respect to time. So relativistic momentum will then combine Newton's definition with the Lorentz factor. So instead of P being our momentum and it's equal to mass times velocity, now relativistic momentum is going to be equal to gamma, which is our Lorentz factor, times mass times velocity. So as our speed approaches the speed of light, gamma is going to get bigger and bigger until it approaches infinity, which results in an infinite momentum. But you really can't have infinite momentum, okay? It's equally impossible for any mass to travel at the speed of light. The speed of light is therefore nature's speed limit, okay? To say that you have infinite momentum would mean that you have infinite energy, which, of course, we know from the second law of thermodynamics, is impossible. Not all the energy that's, there in existence is available to work. There's unavailable energy, energy that's lost, energy that decays due to entropy. And so you can't have an infinite supply of energy. That's actually impossible. So there has to be a limit, and the limit is the speed of light. So while Einstein theory says some things depend on your frame of reference, it also says that some things are absolute, like the speed of light. So if you look at Einstein's theory for predicting relativistic speed, and here's the equation that he uses to do it. So this is for predicting relativistic speed between two moving frames of reference. So frame reference 1 and frame reference 2 each have their own velocity. Notice that if we change the velocities up, that our relativistic speed continues to get bigger and bigger until finally we just approach c. We can't get over c. So if both our frames of reference are moving at half the speed of light, then relative to each other, they're going to see them moving at 80% of the speed of light. If one of those frames of reference then ups its speed to 80% of the speed of light, now both of those frames of reference will see each other moving at 90% of the speed of light. But if either one or both of those frames of reference are moving at the speed of light, then the rate at which those frames of reference will see each other moving is the speed of light. The speed of light is nature's speed limit. So this formula results in two very important ideas. The first is that nothing but light can travel at the speed of light. The second is that no matter what velocity you have in your moving frames of reference, the speed of light in any frame of reference will always have the same absolute value. This leads us back to Niels Bohr's correspondence principle. Remember, the correspondence principle says that new theories must agree with the experimental results from the old theories. So we have to be able to explain what's going on, not just with the new experiments, but also with the old experiments as well. And this is where Einstein's special theory of relativity was shown to be special and not general. Because it does conform to the correspondence principle, but here's the rub. Everyday velocities are such a small fraction of the speed of light that we can just approximate, v squared over c squared with 0. So that part of the term there that we see in the Lorentz factor, we just turn that into 0. Well, when we do that, the Lorentz factor just reduces to 1. And so anything times 1 is itself. So then time equals time, length equals length, momentum equals mass times velocity, just like Newtonian mechanics says they should be. But we get to find that there's a difference when we're looking at astronomical phenomena. So when we're looking at astronomical phenomena, Einstein's theory of relativity will conflict with Newton's theory of gravity. And so that's why Einstein's special theory of relativity is called special and not general, because it only applies to in a certain way or in certain situations. It doesn't apply across the board, which a general theory of relativity would. Of course, Einstein, recognizing this feature, he's like, I got to find the general theory. And he actually worked on that for 10 years before he was able to figure it out and find out, okay, how do we make a theory of relativity that can actually, jive with Newton's theory of gravity. Took him 10 years, but he actually did it. And that's what we'll talk about in the next lecture. So, thanks for watching. Hope you found this helpful, and we will see you in the next video.